And what will happen is that I will wrap up a few things about density estimation, and then after that, Geoff will take over, and he'll tell you more about linear methods and statistics. Okay, so just to recap a little bit from last week, what we looked at is cases where we want to do density estimation, right? Something is beeping here. Outside. Okay, good. So now we know a truck is moving backwards. Great. So one of the things that we had to deal with is, let's say I have a couple of discrete observations, and then of course if I use that for density estimation, it's kind of awkward. So the idea was to smooth it out by some densities, and then there was the question I should explain what the axes are. When I'm talking about densities, this thing will always be P of x, and this thing will always be x. Now, how can I draw x if x is some, let's say discrete set? Well, I can't really, but since I'm not really terribly good at drawing in more than 2 dimensions, you'll have to put up with the fact that this is just some abstract domain. That's just for illustration purposes. So none of the plots are to scale, obviously. The other thing is some folks ask me whether I can put the scans of my handwritten notes up online. I would really rather not, because my handwriting is awful and I feel kind of embarrassed to do so. On top of that, I'm not sure how much you'll be able to make sense out of that beyond what's already on the videos, because the handwriting is really awful. Okay. Were there any questions from last week? Okay.
This is more of an administrative question, but you mentioned there was going to be a
self-assessment, yes.
Self-assessment.
By the end of this lecture, you will find it up online.
Okay.
Okay. It's entirely my fault. Geoff did his part, I didn't do mine. Okay, so this will be there.
It's the same as for 601, right?
This is what?
Same as for the 601.
Yeah.
So the requirements are technically the same as for 601, but be prepared that 701 is a more challenging class than 601.
Yeah, this is sad because there is a self-assessment test there.
Yes.
It's the same self-assessment test, yes.
So yeah, you should, however, struggle less if you want to stay on 701. So if you're struggling with the self-assessment test a lot more, then maybe you should consider 601. And I apologize that I assumed that things like densities were kind of well known, but Geoff will actually cover some of those things probably today. And I was also assuming last week that maximizing the likelihood of observations would be kind of understood overall to be a good idea. So in case this is not, let me just quickly explain what I was doing there. Well, if we have P of x, then, and let's say I have events x and x prime, then P of x being greater than P of x prime means that x is more likely to occur than x prime. I think that should be kind of self-evident. The other thing is that x can either be a countable set or, basically something for which you need to explicitly introduce a measure. And what I'm really always asking is, P of capital X, where this is the, so PR of capital X, this is the measure, right? So in other words, this could be, for instance, if this thing here is an interval going from A to B, this could, for instance, be something like the little p of x integrated from A to B, right? So to drive this home a little bit more explicitly, let's say I have the distribution over, native languages of people here. My guess is probably we'll have about 15 to 20 different mother tongues in this room. So I can explicitly ask, what's the probability of, let's say, for instance, English being somebody's mother tongue? And my guess is it'll be probably less than 1/2. On the other hand, you can, if you ask about people's salaries or incomes or stipends or something, then this is going to be a number that is probably not going to be very much, well, there might be like the CMU standard rate at which it's peaked, but other than that, it'll be, you can more ask something like, what are the chances that somebody earns between $1,000 and $1,100, right? This makes more sense because the chances of me guessing exactly your salary are probably really, really low. But my chances of getting the interval right are pretty good. Likewise for today's weather, for instance, I don't know, it's probably 65 degrees, but is it really 65 or it's probably 65.237 whatever. So you would always then make a statement about an interval. There was a question over there?
So the probability density estimation is the union of the single interaction or Laplace function?
Well, it's okay. So whenever you have a density, and let's say here's A, here's B, and of course this needs to go down to 0 such that it integrates out to 1, then PR of x would be really this area here. Now, if I have a discrete event, let's say, for instance, there's the CMU standard rate of, PhD stipends, and I don't know, let's say it's $100,000. I mean, obviously it is not, but imagine we're all really rich. So, okay, then there would be one delta peak here. So you can mix those two things. But again, you would want to ask, probabilities for ranges in this case. So if you're really interested in those questions, you should really take a measure theory class. This is going very quickly way beyond what we want to cover on 10701. Probably 10702 or 705 might be a more appropriate class for this. The point here is to give you methods that you can use. It would be a lot of fun to go into this, but there's just not enough time. We will encounter one non-trivial case where we have a counting measure and a non-trivial counting measure. So where we basically have, let's say, a domain, which is n0. So basically all the integers. And our measure will be 1 over x factorial. And bonus question to anybody who has an idea what the distribution is that matches this. What? Gamma? Almost. The gamma is the conjugate to what you're looking for. So what's the distribution? You're close. Poisson, exactly. The Poisson distribution is one where I have 1 over x factorial e to the minus lambda x, and then there's some other normalization. P of x is proportional to this, and yes. Anyway, so this is a distribution where you actually get a non-trivial normalization. You could have another distribution where P of x is just e to the minus lambda x, and basically this parameter lambda really determines the shape of the distribution. Okay. So this is really just an aside, and we'll revisit that a little bit when we do exponential families. But for now, just assume that you have a reasonable domain and a reasonable measure. And reasonable means counting whenever we have a discrete set of outcomes, and Lebesgue whenever we don't. So if we have anything else but counting and Lebesgue, we'll tell you. Okay. Good. Any more questions? By the way, this is good that you guys are asking questions. Yep.
I just had a question regarding kernel widths.
Yes.
Is there any value in making it variable for a single data set?
You are spot on. This is exactly what I'm going to do in the next few slides. Perfect. Couldn't have asked a better question. But just bear with me because we're going to do nearest neighbors first. So if you think about what we did last time with the Watson-Adaria estimator, right? We basically got the following estimate. We had that y hat of x was given by sum over all the i's, yi's, and then here I had k of xi and x divided by sum over all the j's, k of xj and x. So these are basically weighting coefficients, wi of x. And of course, you would expect those wi of x to be really large, as in, I mean, of course, they all sum up to 1, but to be relatively large, when x is very similar to xj or xi, and small otherwise. So this is basically a weighted local average, which is yet another explanation of why Watson-Nadaria works. Now let's do something a little bit, well, brutish. And, here's our query. And here are some points around it. And I might get, weightings that go like so. Now, let me use something else instead, namely a weighting that is, 1 or 0, or rather 1 over k and 0. So it's basically all or nothing. Why would I want to do this? Well, because this way my code runs a lot faster. Because if I only have to look at the k nearest neighbors for my query, then obviously I only really need to evaluate things in that neighborhood. If I, for instance, have a fast neighborhood lookup scheme, then I can use that directly. So the obvious question, so can somebody tell me for a 3 nearest neighbor classifier what I would want to predict for the green circle? Okay. Who votes for blue? And who votes for blue? Who votes for red? Right. Okay, so you got the idea. So the 3 nearest neighbor classifier will take all the reds. Now let's say I take a 5 nearest neighbor classifier. Who votes for blue now? Who votes for red? Okay, case closed. I think we know how to do it. Basically, all I'm doing is just I'm taking a hard threshold, and depending on what k I pick, up to that k, I just take all the observations, give them equal weight. Beyond that, I give them 0 weight. This is done mainly for computational reasons, and sometimes it also makes your proofs a lot easier. Yep?
Do you ever do a weighting by a distance?
The weighting by a distance is exactly what Watson-Nadaria does, right? So if you look at Watson-Nadaria, this has exactly this function which is fairly large if the point is close, and it's small if it's far away. If all the points are really far away, they all get the same equal weight because they have to sum up to 1. So the only problem is this way, if I have a lot of data points, my code runs really slow, which is exactly why nearest neighbors can sometimes be a better thing to do computationally. Yep?
In the first equation, the kxi x would be x sub j x.
Correct. So this is what happens if you do cut and paste between slides, because I think you caught me on that very thing last week as well, and I fixed it on those slides, but not on the new slide deck. Okay, thanks. Okay. Any other questions?
What's incorrect here?
So the sum on the in the numerator should be k of xj and x as opposed to k of xi and x. Yeah.
What happens with the nearest neighbor estimator when there's a tie?
Well, when there's a tie, you break it in an arbitrary way, or preferably you pick an odd number of nearest neighbors. Then you don't have ties.
Even for the nearest neighbor case, you have to calculate distance from all the points, right?
If your algorithm is very, very inefficient, then you would do exactly that. You would compute the distances between all the points. So let's. So I don't know whether you've done anything like data structures for spatial data analysis and so on. But let's take a very simple thing. So let's say the data is just in 1 dimension, right? Okay. So here we have all of our observations. They're nicely lined up. Now comes a query. Okay. And I want to find the k nearest neighbors. Okay. Who would go and compute all distances to the query in order to find the k nearest neighbors? I don't think anybody would, right? What you would do is you would sort all the points first. This takes you order in log n. Then you do a lookup, which takes you order log n. And then you traverse that list to the left and to the right, which takes you order k. So in other words, with order n log n preprocessing, you can now serve those queries in order log n plus k, which is quite fast. Now, if you're in 2 dimensions, this is not quite that easy anymore, right? So then you want to have a space-adaptive data structure. You can, for instance, do stuff like, okay, well, let's partition here, then we partition there, 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 and so on. And this is what gives you KD trees. And there are actually a couple of people at CMU, so Alex Gray, who's now a professor at Georgia Tech, and Andrew Moore, who was his PhD supervisor. And they worked on using this idea to accelerate all sorts of algorithms in a very elegant way. So look at that literature if you are interested. However, I think there's actually an even cooler data structure, and it's called a cover tree. And this is by, amongst others, Begelsheimer, Langford, and Kakade. So John did his PhD at CMU. I'm not sure where the other two did, but she is now at IBM. He's at Microsoft. And yeah, he's also at Microsoft. So, and you can actually find code for that. It's a really cool data structure where you have basically something like a tree-based nearest neighbor lookup. The only difference is that it does not necessarily immediately give you all the nearest neighbors, and you have to do a little bit of extra work. It's a really cool paper worth reading if you haven't seen this. This can help you accelerate nearest neighbor lookups considerably. So if you ever need to do this at scale, look at their paper. And then there are all those random projection methods, and just recently the Kanellakis Prize was awarded for that. And you basically want to look at the work of Piotr Indyk. And then pointers from him. So this leads to something called locality sensitive hashing. If you like that kind of stuff, come to my class next semester. We'll be doing a lot of this. Okay. Any other questions? Good. So let's have a look at what it actually performs like. So I basically just took some points from 2 Gaussians, and I drew the red ones and the blue ones, and here's the nearest neighbor classifier, well, which looks horribly ugly. By the way, if I have 2 Gaussians with the same spherical covariance and 2 different means and, well, same mass, what would be the optimal separator? Can somebody tell me the geometric shape of the optimal separator in this case? Yep. Oh, sorry. Hint, it's very easy. Yeah.
Straight line?
Exactly, it's a straight line. If that looks surprising, you should just write out once the case where you have P of x given y equals 1 equals P of x given y equals minus 1. Now, since these are exponentials of, and then some quadratic function in both cases, and possibly with slightly different weights depending on if I have different conditional class probabilities, because I also would need to multiply with P of y here, then you will see that basically you get a quadratic equation. So in general, you'll get parabolas or hyperbolas, basically anything that you can write out with a quadratic function. And in this special case, you just get a straight line. So this obviously doesn't look very much like a straight line at all, right? So But if you squint at it, you realize actually, even though it doesn't look terribly beautiful, it's probably not going to get a lot of stuff wrong. There's a few points on the boundary where it'll probably estimate things wrongly, but by and large, it's actually pretty good. So what this tells us that even though the decision boundary and the estimate in this case is fairly bad, so our model has nothing to do with reality, it will have fairly decent generalization performance. So this is something to, remember many times over. Let's take 4 nearest neighbors. Well, what I've done is I've color-coded essentially the number of, reds or blues, and as you move from the left to the right, you can see how you get more reds or more blues. And if we look at just the sign of it, here's what we get. And the boundary is exactly those points where things are ambivalent. Everything beyond that is either red or blue. Yep?
Here the boundary consists of small straight lines, right?
Yeah, so basically each of the segments is actually a straight line. And that's just what you get by looking at the polyhedra of k nearest neighbors. Again, if that's something you like, you should take a computational geometry class. This is fun to do in low to moderate dimensions. As soon as you move to higher dimensions, it's actually non-trivial. But you could explore it this way. So let's just see what happens if we get the nearest neighbors, if we get more data. So the 1 nearest neighbors, well, if we have a perfect separation, it'll converge to it. But if we have a noisy problem, we'll actually get more error than we should have. Because basically, locally we'll always get things wrong. There'll always be, a fraction of points where the wrong class label, will tell us what it is. Whereas if we have k nearest neighbors, then, we, while needing a little bit more data, will converge to the minimal error. Okay. So here's a little bit more in terms of lookup. So basically, this is what I mentioned before. Essentially, the cover trees have very, very nice guarantees in terms of construction approximation. It's really worthwhile looking at that paper. Okay. Now, there were a couple of questions that came up before. Sorry.
Can you go back to
Yeah.
so how you prove this
Okay.
array?
So here's how you get it. Yep. So do you mind if I answer this question first and then I answer yours? Oh, I'm sorry. I apologize. So basically, how do you prove things like that? Okay, well, let's do it, right? So let's say I have some points here. I have some points there. And let's take the k nearest neighbor case. So obviously, what we want to show is the following thing. So basically what you have to do is you have to assume that the region containing those points will get smaller and smaller, which is fine because what we are going to do, for instance, is let's say we pick k to be order of square root sample size. So therefore, the number of, there's a lot more beautiful and detailed derivations, and I actually had a link on the last slide deck as to where to read this up. But basically, if you have something of that form, then you can see that the region, so radius for any given point, will go to 0 as m goes to infinity. Okay. So furthermore, we also know that the number of points the number of neighbors of x goes to infinity as m goes to infinity, right? Because we picked k equals order square root m. So therefore, we know that the probability estimate will converge to the true probability within that range, within that interval. So we shrink the ball, but at the same time, the number of points that we have inside one of those neighborhoods, well, that goes to infinity. So therefore, we know that the probability estimates within each of those regions is going to, be correct. Now, what then happens is, so this is a very hand-wavy argument and can make that much more formal, but I don't want to do that here right now. So then what that means is that you're going to predict with a majority class. So if you predict with a majority class, well, let's look at the error, right? So let's say the majority class has some p hat of x, right? So with probability p hat, then you're going to get things correct. But with probability 1 minus p hat, we're going to make an error. Right? This is exactly what we get. So this is what my local, because that's basically the probability that, well, the class label is the other way, and so, well, we have it, right? That's basically the claim. Now, if we have a nearest neighbor, just the one nearest neighbor, then the probability estimate will never converge, and it'll always be with probability, p, it'll be, the correct class, and with probability 1 minus p, it'll be the wrong class, and so therefore, that error will be larger than that. So that's the argument. So that's why, as you get more data, you want your scale to increase. Okay. Any?
What does third line say?
Third line is this. Number of neighbors for a given point goes to infinity as the sample size goes to infinity.
So what is the
So this is basically k. So because I picked k to be order of square root m, so of course k goes to infinity as m goes to infinity. M is the total number of points. So as the total number of points goes to infinity, so does the number of neighbors for a given point also go to infinity, and therefore I get convergence within that smaller and ever shrinking region to the correct probability. Furthermore, since the regions get smaller and smaller, my local approximation of the density is going to be closer and closer to the true density, and so that's essentially those two pieces that you need in order to get the optimal result. And so k nearest neighbors is actually one of the first examples of a non-parametric estimator, because the entire statement only hinged upon the fact that I have some distance measure, and that as I get more data, I will converge to the optimal solution, right? So what this tells us actually that given a crazy amount of computation and memory and everything, well, I could stop here, right? And we are done. The point is exactly that, usually we don't have crazy amounts of computation and memory available, so we need to be more clever in implementing the algorithms. And this is the rationale pretty much for the rest of the course. So essentially everything else now is icing on the cake. Okay. Any more questions? Okay, good. So now we get to the point that I was asked many, many times. Well, how can we actually adjust the scale? And this in a way is a chicken and egg problem, right? So, okay, let me specify the problem first. And it already came up in the basically on the discussion groups anyway. So let's say I want to estimate the population density in the United States. Well, then I have the problem that there are some regions where there are cities and a lot of people live there. So basically regions of very high density, and I might want to capture the very fine degrees of density variation. Let's say, for instance, Pittsburgh downtown versus maybe some suburban neighborhoods versus some high-rise buildings, whatever. And on the other hand, I have essentially somewhere in the Appalachians where basically nobody is ever there, and there's a lot of forest, so you have very low density. Now, if I pick a kernel density estimate with a very wide kernel, let's say 1 mile wide, then I will kind of do probably a decent job in the middle of nowhere, but I will completely oversmooth population density variations in Pittsburgh or in Manhattan, right? So there it would fail miserably. Now, this is really bad because in a way it's like, well, if I knew what my density was, I could come up with a really good density estimate. And on the other hand, I need a good density estimate to come up with an idea of what my density is, so it's this circular reasoning that doesn't really help me very much. And Silverman was the guy to whom this name was attached. I'm not sure whether he was the first one to invent it, but that's how I learned it. Essentially, Silverman's rule goes as follows. Let's come up with a very, very cheap proxy of what my approximate sort of kind of density is. And the cheap proxy is that I'm going to take my my k nearest neighbors, and I'm going to pick the average distance among the k nearest neighbors. So the benefit of doing this is that if there's absolutely nothing around me, I'm going to pick a very wide kernel. If there's a lot of data nearby, I'm going to pick a narrow kernel. This is obviously not perfect, but it's much better than not using this. So let me show you, and this will basically give you now a bandwidth which is different at each and every single point that you're going to pick. So let's look at what happens here. So this is a density that was generated by taking two Gaussians, a narrow one and a wide one, right? So on the left, this is maybe Manhattan, and on the right, this is, you know, somewhere in the middle of Kansas. So if I perform density estimation with a non-adaptive kernel, it fails actually in both regions. It will fail for the high density region because it rather very much underestimates it and oversmoothes it. And it'll fail miserably in the low density regions because at some points it'll just put zero density. If, on the other hand, I use an adaptive kernel density estimate, then this is what I get. So, in other words, what I have now is a kernel density estimate where p hat of x is given by 1 over n, sum over I going from 1 to n k of, let's just say, Ri of xi and x, where Ri is exactly this, you know, 1 over k, sum over x in the neighborhood of xi, x minus xi, and then k sub Ri of x prime and x is, and now I need to rescale, so I get Ri to the d minus d, and then here I have some function kappa of, let's say, well, let's just say x prime minus x divided by Ri. So this does exactly what I want then. So quite often you don't quite use that straight out of the box, but you might want to rescale this. So you'll get some coefficient beta here, and of course then, you know, you need to recalibrate by beta to the d. And then this is essentially what you really use for model selection. You want to optimize this coefficient beta such that you just get the scale right. Okay. Yep.
Can I ask, the green points there, those are your actual data?
Correct. The green dots are the actual data. And you might wonder, well, why on earth do they actually oscillate around here? Well, that was just a plotting device of mine to make sure that you can actually distinguish how many points you have there. This is a fairly useful trick if you have, let's say, a one-dimensional density and you want to illustrate how many points you have. If I were to plot them all on this line, you'll just see some green glob down here. But by adding a very tiny amount of noise to it, maybe 0.001 Gaussian noise, you actually get a little bit of spatial variation, and so you can distinguish things. This is overall a useful trick for visualization. If you have a lot of identical objects and you want to illustrate how many of them you have, you make them ever so slightly different to an extent that it's clear that that difference doesn't come from the data but just from plotting. So for instance, I recently ran into a problem where we needed to visualize a lot of circles of different center and different radius. And we had some circles that occurred many times over. So you just give those circles a slightly different center by a tiny little amount. And then you can actually still ascertain how many of those circles you have. So this is a useful meta strategy. Any other questions? OK. Yep. Yes and no. So cross-validation is the outer loop that you will have to run to adapt beta, right? So you'd basically want to adapt this. Well, OK, k is actually overloaded here, but I guess you get the point. So you both need to adapt how many nearest neighbors you want to include. But this is typically fairly straightforward. But then getting the scale right, because you still probably want to explore a scale between 0.1 and 10 of that proposed radius. So this is what you then would use cross-validation for. But you're basically now designing a considerably more complex density estimator, which is already scale adaptive at a lower scale, but you still then need to determine how much smoothing you're going to give this density estimator beyond this local scale. But that was a good question. OK, any other questions? OK. And yeah, of course, this is the distance distribution, and you can clearly see that there are some points which have, not very distant neighbors, and some for which these scales, are very small. So you can see exactly this thing happening. This is the high density region, and there, the radii are very small, and then there are a couple of points that are really far away, and we get a much wider, smoothing kernel. And yes, you want to multiply this then by this beta. Okay. So I guess now it's my turn to hand over to Geoff, and he'll tell you everything about linear methods.
Some fraction of everything.
Well, the other fraction is next week, or on Wednesday. Do you need this?
Nope. Hopefully, not if technology works.
Yeah, famous last words.
Yeah, exactly. Can I have the mic?
Sure.
All right. Layla, could you look and make sure that I have the reasonable levels on the mic? Testing.
Yeah.
Great. that thing about technology working seems to be accurate. Here's the answer. That's always the first thing you should check. There we go. Sorry about that. All right. So, do we have? All right. Cool. We seem to have success. All right. So first thing I wanted to do was to advertise that we're going to have a recitation, which is tomorrow in this room right here, 5 to 6:30. It's going to cover linear algebra review. So I recommend it. It'll tell you all sorts of cool stuff that you will hopefully be able to use a lot in the class. All right, so I'm going to start by going back and doing a review of probability. This may be a review for some of you. For others, it will be very helpful. In any case, I hope it helps people swap the material back in. So all right. So think of some randomness. So the sort of randomness I like to think of is maybe one of your professors throwing darts at a checkerboard. And I'm really bad at darts, so it's more or less uniform which square on the checkerboard I hit. And let's imagine that there's like some kind of plastic tube that keeps me from missing the checkerboard entirely, so we won't have an other option. All right, and think of some randomness that you could imagine repeating, right? So you can imagine me standing there and throwing darts at a checkerboard forever. I wouldn't, but you could imagine it. And for probability, we mean the long-run frequency of different events. And so we have, for example, events like I'm going to hit the top left square of the checkerboard. That happens. So this is a 6x6 checkerboard. Let's say it happens 1/36 of the time. And that's basically all there is to probability, right? So I'll stop here. No, I'll keep going. Now, this is not the only possible definition of probability, right? So if you're into philosophy, you could go and come up with probably as many different definitions of probability as there are philosophers. One other good one that you'll encounter a lot is based on the odds for bets that I'm willing to take. So for example, I'd probably be willing to take a 36-to-1 bet on any one of these squares on the checkerboard, and so that's a good estimate of my belief in its probability. All right, so there's going to be some universe U. Here it's the checkerboard, right? And there are going to be some atomic events, right? So here, right, this is going to be an atomic event. And atomic just means that that's the smallest resolution we're going to think about. We're not going to think about where in the square we hit, right? And then I can make other events out of the atomic events by collecting them together, right? So here's some funky-looking event, right, which are these, looks like 7 squares, right? And I'm going to say now that all squares have probability 1 over the size of the universe equals 1 over 36 here. And so that basically lets us calculate. So let's call this event A, and the probability of A is 7 what? 7 over 36, that's right. Right? The probability of an event in general is the size of the event divided by the size of the universe, right? Size being the number of squares, right? The number of atomic events it takes. Probability of the universe, anybody want to guess what that event? 1, exactly, right? So it's universe, size of the universe over the size of the universe is 1. And anybody want to guess what the probability of not A is? Thank you. So it will be 1 minus the probability of A, right? Which, if you are fast with the rationals on your feet, you get 29 by 36. Okay, so we can write down a whole bunch of useful conventions, right? So we have an event A, and I'm just going to write capital A to be the tuple. Actually, let's write a tuple as angle brackets. A and not A, right? Actually, let's write it as a set. I'm sorry. So because I'm not going to allow repeated elements. So A and not A, right? So by not A, I mean universe set difference A, right? So everything in the universe other than A. And then, so I wrote P of A, right, for the probability of the event A. I'll write P of capital A to mean the table, right, which is P of A and P of not A, right? So in other words, if I have two events that don't intersect and that cover the entire space, right, I can give you a table that sums to 1 that gives me the probabilities of those events. And in general, if I have what we'll call by the euphonious name of a MEP, mutually exclusive and exhaustive partition, right? This is a bunch of sets AI with, right, so we'll call them specifically A1 through AN, and AI intersect AJ is equal to the null set, and the union, sorry, that's not a, that should be a union over I of AI is equal to the whole universe, right? And this here, I should qualify for I not equal to J, right? Because AI intersect AI is typically non-empty. All right, and so given this, right, if I have any mutually exclusive and exhaustive partition, capital A, which is the set of all of the AIs, I can write P of capital A as the table P of A1 up to P of AN. That should be an N, not an M. Right? And so the point here, right, is I can make all sorts of nice probability tables out of that checkerboard by splitting it into a bunch of non-overlapping pieces, right? So I have, here's my horribly drawn checkerboard, and I could take a piece like that, right, and then another piece like that, and another piece like that, and that would be a mutually exclusive and exhaustive partition. Okay? Now, I could take two different partitions, right? So I'll have MEPs A and B. I'll use MEP a lot because it's fun to say. And I can write, so a couple of things. So first of all, I can say that AI intersect BJ, right? So AI is a set, BJ is a set. I can intersect them. All sets are events, and something interesting happens, right? So here's my checkerboard again. Here, let's say that AI is this row. And let's say that BJ, right, this is BJ is that subsquare, right? And then AI intersect BJ is this thing, right? And so I can assign a probability to that. And that's the probability that both of those events happen at the same time, right, on the same throw of the dart, AI and BJ. And I can make a probability table of both A and B together. And the elements are going to be P of AI and BJ, right, for all I and j. Okay, so the data type of that is it's a table, right? It's not just a single number. Now, I should warn you, I'm going to try and be careful during this lecture at least to follow the convention that a capital letter stands for a set of possible events, and a lowercase letter stands for an individual event. But I should warn you that that convention is not always followed. Maybe not here, depending on how careful I was with the lecture notes, and definitely not outside of class. So it helps when you're looking at a probability expression to think, did the author mean probability of a single event? Did he mean a table of probabilities, right? And it gets even crazier when you start talking about other types of probabilities like probability densities, random variables, all of these things, which I'll cover in a few slides. Okay? Questions so far? Okay. So I already mentioned this, right? So I can take A and B, right? So actually, I guess I'll write it for individual events. You could generalize it for partitions, right? And A or B, and that's the same as A intersect B. Oh man, my handwriting's worse than usual. Intersect B and A union B, right? And either the logic notation or the set theory notation is OK. In this case, they're just synonymous. And in fact, a lot of notions of logic are built on top of set theory. OK, so conditioning. So let's say we have some weird event B, right, which looks like this. Right, so there's a weird event B, right? And then let's just say that the A's up are the rows of the checkerboard, right? So you can imagine that I throw darts until I hit this region B, and then I ask you which one of the A's happened, right? So anybody want to guess what the probability that I get A2 is? 1/6. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? Did I get that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So probability of A2 will be 2 over 13, right? Which is equal to the size of A2 intersect B divided by the size of B. So I'm going to assume that the people who said 1/6 just counted 12 instead of 13. Yeah? OK. How about the probability of A1 given B? 0, right? Because it's impossible. They don't intersect. And in general, right, you get this formula. This is called the probability of A2 given B. And what is the probability of B given A1? Any good ideas? Somebody said 0. I'm going to go with not number, right? Because the probability of b given a1 would be oh no, you're right. B given a1 is 0. Sorry. So what I meant to say was, suppose you condition on an event with 0 probability. What happens? And I gave away the answer. It's not number. In other words, conditioning on saying, OK, assume the moon is made of green cheese. Stuff of philosophy, not the stuff of machine learning, right? And I can take all of these conditional probabilities. Again, if I have meeps A and B, then I can write P of A given B. And that's the table of all of the conditional probabilities for all of the possible conditionings. In other words, condition AI on Bj. Right? The table of all of that over all I and j. OK? Now, there's this maybe obvious sounding, but actually quite useful theorem called the law of total probability, or the sum rule. So let's say again that the A's are the columns, A1 up to A6, right? And we have some event B, right, which looks like this, right? So this is B. OK, and I can say then that probability of the event B is equal to, well, I can split the event B according to the events A, right? I can split it into 2 parts along this wavy line. And the probability of B is equal to probability of A3 and B plus the probability of A4 and B, right? And in general, for any meep A, P of B is equal to the sum over I in A. We'll call it the sum over AI in A, the probability of B and AI. OK? So that lets you prove a whole bunch of useful things, like, for example, that the column sums of a conditional probability table are 1, right? So you remember, so this thing here, this table of conditional probabilities, unsurprisingly is called a conditional probability table, or CPT. And so a useful exercise would be to prove to yourself that the sum over I of P of AI given B is equal to 1, right? For any event B and any exhaustive partition A, which is the AIs. OK? So we're not going to collect or grade that, but at least not yet. But that's, if you want to check your understanding, that's a good thing to try. All right, marginal probabilities. These are not things that are almost probabilities, or not very good probabilities. These are, suppose that we have 2 different sets of random variables, right? So let's say that B is the columns and A is the rows of the checkerboard, right? So this is B1 and this is A1. All right. Wow, my drawing's worse than, OK, there we go. But you get the idea. So you can just forget about a particular random variable, right? So you start out with the joint probability table, P of A comma B. And I ask you, what is P of A? Well, you could either calculate it directly, or you could take this joint probability table and sum out all of the B's, right, using the law of total probability. So in other words, so P of AI is equal to sum over J of P of AI Bj, right? And so what I'm doing is just for each for each column here, sum out all of the entries in the column to make the total probability. Sorry, I said marginalizing to get A's. So for each row, I'm summing over all of the entries in the row to get the probability, total probability of that row. Okay. So that's probability in a nutshell. I just wanted to go through and remind everybody of these concepts because we've been hitting them already pretty heavily in these 2 lectures. Are there questions so far? All right. Sounds like this is review for most of you. Yes. Yeah. Okay. So the thing which is probably not review is what happens when you deal with a possibly infinite universe. And that's actually, like Alex mentioned, well beyond the scope of this class. I put a bunch of nice links here for you. This is a textbook on measure theory that is a traditional course for statistics classes to use. If you want to have some fun and bend your mind, go click on the wiki link for the Borel-Kolmogorov paradox. Let me just give you a little flavor of it. So if you have an infinite universe, you can have a mutually exclusive and exhaustive partition with infinitely many elements in it, right? And you could ask, what are the probabilities of all of the elements in that mutually exclusive and exhaustive partition? Well, suppose that they were all bigger than epsilon. Then infinity times epsilon is still infinity, so it would sum to infinity, right? So that means you can't have them all be bigger than epsilon for any epsilon. So you must have, right, for any epsilon, you must be able to find some events that have probability less than epsilon. So actually what's typical is that you'll have many, many events for which the probability is 0, right? Like, for example, you imagine picking a random person in the room and measuring their height. The actual height is, neglecting Planck's constant, a real number. And so there's 0 probability of any specific real number, right? Even weirder, there are going to be some events to which you can't assign a probability at all, right? You should look up, there's this thing called the Banach-Tarski theorem. So these are fun ways to waste time on Wikipedia. Not that there aren't a million other such. But there are going to be some events that you can't even assign a probability to. The set is just such a weird set that it doesn't make sense to assign it any number between 0 and 1. So now that I've told you that, all of the time we go and condition on the data we observed, right? We say, OK, I got some data. I'm going to condition on it. I'm going to think about, for example, what might be true about the model, right? Suppose that data has a real number in it. The probability of the data is 0. And I just told you conditioning on 0 gives you a division by 0 error, right? So if that doesn't blow your mind, well, fine. It blew mine when I first started thinking about it. But that's what the Borel-Kolmogorov paradox is. It turns out that because of this division by 0, not number error, that unless you're really careful about how you define conditional probabilities in an infinite universe, you can get 2 different answers for the same conditional probability depending on how you calculate. So you should be worried about it, but you shouldn't be that worried about it. In the sense of, for the rest of this course, I'm just going to pretend everyth's pretty good, right? And we're going to do all of these calculations as if conditional probabilities meant something. And if you ever start to lose sleep about it at night, go read up on the Borel-Kolmogorov paradox and what its solutions are. But for now, stop worrying and learn to love the density function. So a density function is the analog of a probability distribution in an infinite dimensional space. It's basically if you replace sums to 1 with integrates to 1, and replace sums with integrals in every one of the slides that I've already presented, everything turns out to hold, unless you get really unlucky and hit one of these paradoxes, right? So the density is just any function p of x such that the integral over your universe of p of x dx is equal to 1. For example, conditional probabilities still work, right? The probability of A and B is equal to probability of A given B, and I'll put the divided by over here, probability of B, right? So you can still define this conditional probability as the joint P of A and B divided by the marginal P of B. And it works, right? And the only thing is that, densities are infinitesimal probabilities, basically, right? And so what you're doing is comparing various flavors of 0 to one another. And again, don't worry about it so much, and just, it'll work unless you get really unlucky. And so some good examples of continuous distributions are the uniform distribution, which has density 1 over b minus a between a and b, and 0 outside that. So check your calculus and make sure that that integrates to 1, right? And so it looks like this. Or here are a bunch of Gaussian distributions. This formula, you'll learn to know and love it by the end of this class if you don't already. It looks like this. You can change the sigma, which is the standard deviation, to make it wider or narrower, and you can change the mu to shift it left or right. All right. You can also have multivariate densities, right? So this is 2 continuous random variables, right? And so just like I had a 2-dimensional table when we did the joint probability of 2 discrete random variables, a 2-argument function is the infinite analog of a two-dimensional table. And so, p of x comma y is just a function from R2 to R, right? So instead of just a table which is, has both rows and columns. All right. Random variables. So I've been talking about mostly events so far, right? Events are things that either happen or they don't. I could go through and write a label on each one of these squares, right? So I could say that I have some set of people in a room, and I'm going to pick a person out and measure his or her height, right? And perhaps it's 5 feet even for these guys, right? And, so we'll go like that and say that all of those people are 5 feet even. These people are 5 inches tall, apparently. This is 5 feet, right? Right? And this should be 5 foot 6 inches, right? For all of these guys, right? Like that. And I could keep on doing this, right? And partition this into a bunch of areas where people are different heights. And let's say there are only 5 distinct heights in my room, right? And so more formally, right, a random variable is just a function of the atomic events. Right? And so here, right, the function is the one that says 5 foot if you happen to get any one of these events, right? But you could have a different value for every one of your atomic event. So it's a quantity that just depends on which square we picked. And we can use whatever our favorite data type is, right? We could use real numbers. We could use true, false. We could use integers 0 through 9, right? And those are all random variables. And then the random variables turn the turn the space of all turn the universe, the space of all possible atomic events, into so x equals height is my random variable, so I can say x equals 5 foot 6 inches. That is an event, right? Because it defines a set here of cells in the universe. Okay, and so I'll write in general capital X equals little x for a random variable, which I'm going to use capital letters for, and a particular value, which I'm going to use lowercase letters for. And again, warning, that convention is not universally followed. But it's useful to, again, think to yourself which the person means when they're written. All right. You can have many random variables, right? Height, weight, shoe size, mother tongue, right, of the people in the room. And any function of the random variables, do we need a new type for that? How many people think yes? Or no? People are unwilling to vote. How many people never vote in anything? Okay. The answer is it's the same type, right? So if you have two functions that each take the particular square as input, and then I do another function on top of them, it's still a function from what square to some number, right? So it's still a random variable. So what that means is that we only need to ever think about one random event in the world, which square in our checkerboard we got. And then everything else is either a deterministic set or a deterministic function, right? An event or a random variable. So for probabilities, you know, probability might be hard, but at least you only ever need to think about one random event. Yeah, it helps. So for example, you know, if I take 703 times the my weight in pounds, times my weight in pounds, divided by my height in inches squared, right? That's some function of two random variables, weight in pound and height in inches. And that is itself a random variable. Seems like kind of a useless one, but it's actually one that people have written a very large number of papers about. It's called the body mass index. It's supposed to be a coarse indicator of whether you're at a healthy weight. I will not disclose mine. All right, so right, as a corollary, we only need, like I said, this one set of atomic events together with a bunch of sets and functions defined on it. In order to do reasoning, logical reasoning, right, it needs to be the case if I take event 1 and event 2, it's still an event, right? And if I take event 1 or event 2, it's still an event. And so if my list of sets is closed under union, intersection, complements, it's called a probability space or sometimes a sigma algebra, right? Probably not going to use that term very much, but you'll run across it in a lot of papers. All right, so we have just a few minutes left. I'm going to get to the single most important thing that you'll probably use in this class, right, which is Bayes' rule. So Bayes' rule, you've probably seen it before, but it's really easy to derive, so I'll just go ahead and do it because some of you might not have seen the derivation. So the definition of a conditional was that probability of A given B is A and B over B as long as B can occur, right? So let's multiply through by P of B. We get P of A given B, P of B is equal to P of A and B, right? This, I don't actually even have to write this little codicil here, right? Because if probability of B is 0, well, then this left-hand side is 0, and then the right-hand side is 0 because the probability of A and B can only be smaller than the probability of B, right? And so I can just get rid of this. And for that reason, some people take this as the definition of a conditional probability, right? Now, I can also swap the roles of A and B, right? So I can write this is probability of B given A times P of A, right? And now let's just divide through by P of B. So we get P of A given B is equal to P of B given A, P of A over P of B. Again, now P of B has to be not equal to 0, right? And this here is the ever-famous Bayes rule. I should point out, by the way, that it's a good idea only ever to condition on events that you have some chance of observing so that you don't get division by 0 in your Bayes rule. And as long as you follow that rule, you're probably in pretty good shape. So why do we care about Bayes rule, right? It turns out to be incredibly useful. Suppose that I write that A is equal to my model, right, and B is equal to my data, right? So I take B as the event that I observed some particular data, A as my the event that some particular model is the right one to describe the sampling process that gives me the data, right? So what this says here is I can get, on the left-hand side, the probability of the model given the data, right? And on the right-hand side, I have a bunch of other quantities that I can get it from. So this is the probability of the data given the model. And, well, what is a model? A model is something that tells you the probability of the data given itself, right? So this is like the definition of a model. So I should have that if I'm doing inference, right? P of A, this is the probability of the model before I see any data. That's usually called the prior probability. It causes a lot of controversy, but it's actually often pretty easy to write it down. Probability of B, that's usually called annoying. But there are ways to get around it. And so what you get here is a rule that takes known quantities on the right-hand side and gives you the quantity that you care about on the left-hand side, right? And that's why 90% of machine learning is various applications of Bayes rule. Any questions? All right, we'll start up again on Wednesday, and don't forget about the recitation tomorrow, 5 p.m. right here.